Okay, so last section for this week is section 5.5, and this will also finish up chapter 5 for us. So the first thing they mentioned is the change of base formula. We already kind of went through it yesterday. We didn't need it, but we were doing a problem where it applied perfectly, so that's why I kind of showed it to you. So the idea is if you have a log and the base is not 10 or e, you can't type it in by just pressing a single button. You have to rewrite it as a fraction. Okay, and there's two ways you can rewrite it. You can either rewrite it with common log or natural log. But either way you rewrite it, it's log of the argument divided by log of the base. Just stick with the same log. If you want to do all common log, I would always do it that way. If you want to do natural log, I would just always do it that way. Whichever way you want to do it. All right, so let's use the change of base formula to type that into the calculator, get a graph of it, and then find the domain and range. All right, so that's a base 3 log. Can I type in base 3 just by pressing a single button? Okay, no. So now I've got to rewrite it as a fraction. Can anyone tell me what would go in the top? Leo?
Log of x.
Log of x. And in the bottom?
Log of 3.
Log of 3. Now he didn't say whether he meant natural log or common log. It doesn't really matter which one. I just went with common log. Okay. And now I'll type that in. So we've got log of x, close your parenthesis, divided by log 3, close your parenthesis. Let's do zoom 6 because we've never graphed a log before, so we don't really know. Actually, we might have, yeah, we did graph logs. Not by hand, but we did graph them on the calculator. So we should remember there's a vertical asymptote. So that really doesn't start on the y-axis at -2. It looks like it does, but if you zoom in, you'll definitely see it's going lower than -2. It's going to look like it stops somewhere else. Now it looks like it stops at -3. All right. So it's becoming so steep that the calculator can't sketch it. All right. So what's the domain there? How far left and right does that graph go? Megan?
0 to infinity.
Yeah, it's 0 to infinity, never reaching 0. It is a vertical asymptote on the y-axis. Now the asymptote isn't always on the y-axis, it can shift, but if you don't shift it, it's on the y-axis. 0 to infinity. How about the range? How far up and down does that graph look like it's going to go? Yeah?
All real numbers.
Yeah, it's all real numbers. If you go to your table and plug in a number very close to 1, or very close to 0, you'll see that it does just keep dropping down. And as you head further and further to the right, the y value just gets higher and higher. But look how big of a y value I typed in. 9,999,000. And the y value is only at 14. So it's going up, but it's really slow. So there's your domain and range of pretty much every log function, unless you shift it. Now, shifting left, right, up, or down won't affect the range. Because if something goes up and down forever and you shift it up 1, it still goes up and down forever. But the domain can be affected by shifting left and right. Certainly shifting up and down wouldn't affect domain. But stuff left and right is important. Okay, so all the transformations that we know still apply. Okay. So just as a reminder, A is your horizontal shift, B is your horizontal stretch. All the horizontal stuff is inside, and then the stuff outside the function is your vertical. Multiplication is always a stretch, so C is a vertical stretch. And then addition or subtraction is always a shift, so D is a vertical shift. What would happen if C was negative? Anybody remember C or B? It would cause what to happen?
Reflection.
A reflection. Since C is the vertical, if you make C negative, it's a vertical reflection. Vertical reflections, going to be careful. If that was your image and that was the reflection, that's a vertical reflection. It's over the X. B is your horizontal. If B was negative, that would be a horizontal reflection. So that's left to right. A reflection left to right is over the y-axis. All right, so the first one here, not too bad, just one transformation really. And it doesn't really matter what the base is. Whatever the base is on the function that's transformed, that's going to be the base you're comparing to. You'd never compare like a log base 3 to a log base 7. You compare base 7 to base 7, okay, to keep things equal with this kind of problem. So we have a negative. We just said that negative is a reflection. And can anybody tell me what letter, looking at what we have up above, what letter is negative there? Leo?
B.
B. So that's a horizontal reflection. Okay? Or you could say a reflection over the y-axis. So how can that be graphed? Let's write that down first. Right, so to graph log base 3 of negative x, take log base 3 of x and do a mirror image, or do a reflection over the y-axis. That's the first thing. The next thing is find the domain, range, and vertical asymptotes. Well, let's think about the range first. The range of the original log function is it went up forever and down forever. If you reflect it, in fact, it doesn't matter which way you reflect it. If you do any kind of reflection, would it have an effect on the range? Would that? No. So the range is still going to be up forever, down forever. But when we graphed log base 3 of x, it looked kind of like this. So picture a horizontal reflection of that. What would be your domain now if you mirror image that over the y-axis? Wouldn't be 0 to infinity anymore. What would it be? Dylan?
Negative infinity to 0.
Yes, negative infinity to 0. Negative infinity to 0. It'll never reach 0 because there's a vertical asymptote. And it'll also never reach negative infinity. And I think, find the domain, range, oh, and the vertical asymptotes. I'm going to put up a reminder in a minute if you don't remember how to find the vertical asymptotes. But all you have to do is set the argument equal to 0. Which, in this case, since you didn't shift left or right, the vertical asymptote doesn't move. Right? Vertical asymptote was on the y-axis. So if you mirror image it over the y-axis, it's still there. It didn't move. All right? So vertical asymptote, x equals 0. And again, if you're like, well, how would you figure that out normally? You just take the argument, set it equal to 0, and solve. Okay? And of course, if you solve that equation, you get x equals 0. Okay, once you put a plus or a minus inside the parentheses with the x, that's when it's going to change the vertical asymptote, because that'll shift left and right. And that's it. So any questions on that? All right, let's look at this one. All right, first thing, if I look at the log 3 minus x. How should we write that so that it looks more like that format? What should I do to fix that? You don't have to do this, but I think it'll, if you do, it'll match up with what I wrote on the other page a little better. Yeah?
Put the x in front, so negative x.
Yeah. And Shauna, how many transformations are happening in the negative x plus 3? 2. Yep, there's 2. So first transformation, you would deal with the plus 3. Gracie, what's plus 3 going to do?
Horizontal shift.
Horizontal shift, which way?
Right.
Let's see, plus 3 left.
Oh.
Yeah, so the horizontal stuff is always opposite. So that's going to shift left 3. And then the negative we just had in the last problem. That's a horizontal reflection. Or what axis is that again? If you reflect horizontally, it's over the y-axis. Okay, so how can that be sketched? That's it. There's the 2 steps. Okay, any questions on that? Okay, do they want us to make a sketch? No? Just how could you sketch it? Right, now we'll make a sketch. So when graphing log functions, it's always good to find the vertical asymptote because that kind of tells you your starting point. And the graph of a log always bends away from the vertical asymptote. Could either bend away that way or that way. Now, as far as finding intercepts, if a graph goes up and down forever, what intercept are you guaranteed to always have? Leo?
X-intercept.
You're always going to cross the x-axis somewhere. As far as a y-intercept, you might not cross it. Look at the last graph. This graph, we didn't sketch it properly, but it would look something like that. It would never cross the y-axis. So when I say find the y-intercept, if applicable, if you can, you might not be able to. But you should always be able to find the x-intercept. To find your x-intercept, you plug in 0 for y. Okay, we've written that before. To find your y-intercept, you plug in 0 for x. To find your vertical asymptote, that's a little new, so I'll write that one down. Set the argument equal to 0 and solve. Actually, I already have those written down. So that's how you find your intercepts. And the way you know if you don't have an x or a y-intercept is if you try to plug in 0 for one of them and you get an error. The only one that would ever come up to an error is when you're finding the y-intercept, not the x. Let's see. All right, I usually find a couple points after that because I want to get an idea of the curvature of the graph. But remember, your graph only goes in one direction. So once you find your vertical asymptote, your graph is going to be either values from that asymptote bigger or from that asymptote smaller. It's only going to be one or the other. Any questions on that? So it's really nothing new. Just graph like you always do. Just find some points, make a table, and graph the function. All right, so let's sketch that one. And then after we sketch it, we'll find the domain, range, and asymptotes. Right, let's start with my vertical asymptote. Just because to make a sketch, I really need to do that anyway. So even though it's the second part of the problem, let's do that right away. What would be the equation I set up to find the vertical asymptote? Caleb?
3x plus 5 equals 0.
Yep. So 3x plus 5 equals 0. Okay, so x equals negative 5/3. What would that be as a decimal? Only because when I graph, decimals are a little handier to plot. It's negative 5/3 as a decimal. Dylan?
Negative 1.66.
Yeah, so we'll just say about negative 1.7 just for graphing purposes. But if I ask you what the vertical asymptote is on a test question, just leave it as a fraction. Only change to decimal if you need to graph for your own benefit. Okay. All right, so we've got that. Let's put that in. All right, so negative 1.7. As always, I'll do the vertical asymptote dotted. Make it a little thinner. So negative 1.7, maybe about right there. All right, so we got that. Now, let's find my Y-intercept. Okay. Or we'll try. Maybe it doesn't have a Y-intercept, but I think this one does. So to find the Y-intercept, plug 0 in for x. Okay, let's see what we get. So we get log base 2 of 3 times 0 plus 5. So log base 2 of 5. That I definitely need a decimal so I can graph it. So log 5 divided by log 2. Okay, so we get about 2.3. Okay, so this is going to cross the y-axis at 2.3. Let's plug 0 in for y, and now get the x-intercept. So 0 equals log base 2 of 3x plus 5. Easiest way to solve that is to change it from log form to exponential. Trevor, what's my base there? 2. Logarithm always equals the exponent. And what's on the other side is the argument, 3x plus 5. Okay, Abby, what's 2 to the 0? 1. Minus the 5. And divide by 3. So x is negative 4/3, or about negative 1.3. So that's where it's going to cross the x-axis. Right about there. So I can get an idea of what the curve is going to look like, but what I'm going to do is just find a couple more points. Okay, and I'll do them quick by hand. I'll type in like 5 and 10 for x. I'm not even going to use the table on the calculator. So if I type in 5, I would get 3 times 5 is 15. 15 plus 5 is 20. So it'd be log 20 divided by log 2. So at 5, my graph is at 4.3. And I'll do 10 just because that's the edge of my graph. 3 times 10 is 30, plus 5 is 35. So log 35 over log 2. All right, so log 35 divided by log 2. So 10, 5.1. 10, 5.1. Good enough. So remember, it's going to come down and get pretty vertical near the asymptote. So it's going to look kind of like that. Okay, domain is going to be every number from that asymptote to the right. Can someone remind me, what was the asymptote again as a fraction? It was negative
5/3.
5/3. So the domain, thank you, is negative 5/3 going to the right forever. Range. Well, what's the range of any log function, no matter what? Yep.
All real numbers.
It's always negative infinity to infinity. I think we did it all. Sketch, domain, range, asymptote. Is there a horizontal asymptote in a log function? No. It never stops going up. It always keeps increasing slower and slower and slower. So what's actually happening is the slope of the curve is approaching 0. As you head towards infinity, it's going to start to get flatter and flatter and flatter, but the slope will approach 0. It'll never reach it. And then as you start to get closer and closer to your vertical asymptote, your slope is almost vertical. Okay. Again, never really vertical, but getting closer and closer to it. All right, so last thing we'll look at is a word problem that uses a log equation. And the word problem is going to involve the formula for the intensity of an earthquake as measured on the Richter scale. So the Richter scale is a logarithmic scale, which means that if you had an earthquake of magnitude 2 compared to magnitude 3, the magnitude 3 earthquake is 10 times as powerful. Okay, so each jump in the Richter scale is a factor of 10. So if you compared a magnitude 4 earthquake to a magnitude 2, that's 100 times more powerful. Magnitude 5 compared to magnitude 2, it's 1,000 times more powerful. So each number in the Richter scale, factor of 10. pH in chemistry works the same way. pH of 5 versus pH of 3, it's 100 factor difference. I forget if it's acidic or basic, but. So in that formula, R measures the magnitude. A is the amplitude of the vertical ground motion in micrometers. T is the period of the wave, the earthquake wave in seconds. So these are all factors that just measure and describe the earthquake. And B is a factor that accounts for the weakening of the wave. Because obviously, as wherever you have the epicenter of an earthquake, as it propagates out from that, it weakens. How quickly it weakens, well, maybe it depends on the soil type and different things. Those are all the variables. Okay. Any questions on the formula? All right, so what we're going to do is we're basically going to prove what I just said. We're going to prove that if you have an earthquake that's 10 times as powerful, that it's a difference of 1 in the Richter scale. Okay, so it says, at the early stage of an earthquake, the amplitude of the vertical ground motion was A. At a later stage, it became 10 times as much. I want to know the difference in intensity on the Richter scale. Everything else is going to stay equal. The period of the wave stays equal. The factor that accounts for the weakening of the wave, that stays the same. Given all else equal, if the vertical ground motion increases by a factor of 10, how much would the intensity change on the Richter scale? Now again, we already know it should be 1. But let's go through and figure that out. So first of all, we're trying to find a change. If you have a value before and you have a value now, what do you do with the two values to find the change between them? Like I said, the temperature in the morning was 30, temperature now is 40. What do you do? Yep.
Subtract.
Yeah, you subtract them. And we're going to subtract them bigger minus smaller, so we get a positive change on the Richter scale. If you do it the other way around, it would go down 1 unit on the Richter. But let's take, what did I call the more powerful one? Later stage. So we're going to take intensity at the later stage minus intensity. I don't know what I called the at the early stage. So intensity later minus intensity early. Okay, so let's plug in and see what happens. So the intensity at the later stage. We know the amplitude is going to be 10A, but we don't know anything else. T is going to stay as T, B is going to stay as B, but plug in 10A for the vertical ground motion. So it's log 10A divided by T plus B. Now, when we do the intensity earlier on, what's the only thing that's going to change in the equation from the intensity later? One thing. Everything else is going to stay the same.
You're going to take away the 10?
We're going to take away the 10, and it's just going to be A. So log A over T plus B. Again, all else equal here, we're assuming the factor for the weakening of the wave, the period of the wave, that's all staying the same. Right. So now, whoops, that plus B, yep, that's fine. Actually, I should move my parenthesis just to make this clear. Right. Did anybody see something that's going to cancel out right away if you subtract that expression on the left from the one on the right? So you have log of something plus B minus log of something. And to be clear, I should put brackets around that. So you're subtracting the first intensity minus the second one. Yep.
B cancels.
Yeah, the B cancels, and it's important. I did forget those brackets, but you should put them in because it's a distributive. The B is going to be gone. So you have log of 10A over T minus log A over T. Okay. The B is gone because you distribute it. You'd have negative B plus B, gone. Okay. Now, I have the log of a quotient. Can someone remind me how the log of a quotient splits? Yeah? Exactly, subtraction. Log of 10A. And now watch what's going to happen here. Minus log of T. That's the first one. Minus. And now it's going to split as subtraction again. Log of A minus log of T. Now, does anybody see something else that's going to cancel out there? Yep.
Log of T.
Log of T. Because you'd have log 10A minus log T minus log A plus log T. So the minus log T plus log T is gone. So now, and it should be because those factors were the same. So the B shouldn't have any effect because that stayed the same. The T shouldn't have any effect, that stayed the same. The only thing that changed was A, and that's the only thing that's left. Let's recombine that into one log. How does subtraction recombine? Try to make those look like ones. How does subtraction recombine? Yep. Division. log of 10a divided by a. So it's 10a divided by a. And what happens inside the argument there? Yep. The a's cancel. And now all you're left with is a simple calculation, the log of 10. Well, if you type in log of 10 on the calculator, you get 1. So we just proved that if the vertical ground motion changes by a factor of 10, that's a change in 1 on the Richter scale. Any question on that? All right, so you might see a problem in the homework a little simpler than that, where they just give you parameters for an earthquake, you plug it in, you find the intensity. Okay. All right, so the homework is 301. So it's pretty much all single problems except 8 through 11. So it's 1, 5, 8 through 11. 16, 17, 23, 25, 28, 32, 42, 52. Okay, so we'll take a look at that tomorrow. Tomorrow we have class, it's periods 2, 4, 6, 8. So class same time tomorrow. We'll review that, review any other questions from the material on the week, and then that'll be it. So no tests this week.